Welcome. We are currently working on the stoichiometry unit that we get to start out with in AP Chemistry. Normally I would do this later, but since you've already had pre-AP in general, we're going to forge ahead and get some of these concepts under our belt. Now, in the next two problems that we'll be working on, I would say one of them is a review, and one of them is a little bit of a twist on how to use Avogadro's number. Now, let's first look at the twist. I know that seems odd. Why don't I start with the one you're more familiar with? But the twist is only one step. So I want to start with a one-step problem. And this is a double unit. I hope you remember that from pre-AP, but don't worry if you don't. We can work on it together here. And there's one key to using the double unit concepts. And that key is how you set up the beginning of the problem. Now, we have a double unit here. The way we can write that is we have 142 kilojoules equal to 1 mole. And what we need to do, what the question asks us to do, is convert the kilojoules to joules. I hope that's pretty straightforward. And we have to convert the mole to, oh man, I'm not sure. Let's see if we can read the question and get a better idea, because this is often an implied concept. Do you notice here that it says in joules required to break each bond? So what the question is asking is we have a fluorine-fluorine bond, and we can use energy. It takes energy to break bonds. It's like a force of attraction. And we want to break that bond. This gives us per mole of bonds. We want to know the energy per bond. Now, often the answer would be reported as just joules. Now, I would prefer to report it as joules per bond, but that's not always going to happen. So in this case, you had to read this very, very carefully to figure out what we were doing. So let's put our given here. And again, here's the key to doing these double units. We want to put the 142 kilojoules in the numerator, and we don't want to write it slashed like it's done here. We want to put the 1 mole in the denominator. And if you do this, then you should have good luck with the rest of the problem. If you put slashed units in the top, I think it's going to set you down the wrong path. Now, I'm going to change moles to bonds. So I want to get rid of moles. They're in the denominator here. To eliminate them, I'm going to put them in the numerator. And I want bonds. Well, a bond is a count of something. So remember, when we are counting, we use Avogadro's number. That's why I call him Count Avogadro's number. All right, so there's a 1 in front of the mole, and then we have 6.02 times 10 to the 23rd bonds. So now, if we check our units, I've eliminated my moles, and now I need to convert the kilojoules to joules, and I'll be done. So let's focus on that one. We have kilojoules in the numerator. To eliminate kilojoules, we'll put kilojoules in the denominator, joules in the top. For every 1 kilojoule, I have 1 times 10 to the 3rd joules. And now we always double check that our units are going to cancel. Kilojoules cancel. When all is said and done, I have joules per bond left in my answer. And that answer is 2 sig figs, 2.36 times 10 to the minus 19th joules per bond. So each one of these fluorine bonds would require that amount of energy. Now later on, we're going to see that electromagnetic radiation can be used to break that bond, and so we'll convert that energy into, say, a wavelength of light. But I think that's a good start for this. Now let's take a look at You Do It 4. In this example, this student has an 8.2 ounce can of Red Bull, and we want to know how many molecules are in this can, assuming we have 80 milligrams of caffeine. Now, I don't know grams directly to molecules. We're always going to go through the heart of chemistry, because if you skip steps, you're very likely to invert a ratio incorrectly. So it's better to be thorough than to lose all that partial credit. So I have to get to grams. If I can get to grams, I can get to moles. If I can get to moles, we can get to molecules. So let's start with our original given. I've got 80 milligrams. I'm using the railroad method this time because it takes up a little less space. You can use the parentheses and the multiplication. It's totally your choice, but you do have to set these up as a dimensional analysis. So there's my conversion for my milligrams. Milligrams cancel. Now, mass to moles use, we just saw this in the first few examples. Mass to moles use molar mass. And I'm going to presume at this point that you can calculate 8 times carbon, 10 times hydrogen, 4 times nitrogen, 2 times oxygen, and come up with a molar mass of 194.19. You're actually often given molar masses in the context of questions because it makes it a little faster, and if we're not testing for that concept, we give you that information so that we can zone in on the concepts we're after. Now I want to get rid of moles and I want molecules. Molecules are a count. When we are counting, remember, we use Avogadro's number, 6.02 times 10 to the 23rd. Now, if we do that math, we would end up to our original 2 sig figs with 2.5, assuming I plugged this in right, 2.5 times 10 to the 20th molecules of caffeine racing through his or her body as they try to pay attention to class. Now let's move on to one more concept. We have time to do at least one more in this video. So let's go to atoms within a molecule, or really we've already seen ions within a formula unit. And what we'll primarily use are subscripts. Now there are some quote unquote within problems that we'll do that won't use a subscript, and those are hydrates. If we're trying to find water within, what we're going to be using is the hydrate number, which is actually a coefficient. But by and large for these, we're going to be using our subscripts for those. So let's take a look at the first one. How many atoms of carbon are present? Now, again, we have grams and we're going to that count. So we need to get to moles, and that shouldn't be too tough at this stage. Now, once we have moles, there's 2 directions we can go here. We can go moles to molecules and then molecules to atoms. Now, the relationship that coefficient gives us is not only at the atom to molecule level, but it also holds true at the mole to mole level. So we can go moles of sucrose and we can get to moles of carbon, and then we can go atoms of carbon. I'm going to do this one in this direction, and then another one I'll do in the other direction, so that you can see that this subscript tells me that not only do I have 12 atoms equal to 1 molecule, but that I have 12 moles of atoms equal to 1 molecule. So those coefficients can be counted at both the atom and molecule level and the mole level, and which you choose really doesn't matter. So let's set up our dimensional analysis. Set up my little railroad here, my little grid. And we're going to start with our original given of grams of sucrose. Now you want to label this so you don't get lost in the map, but I'm okay if you would label that with just a SUC for sucrose. When it's a long formula like that, it's okay to do that as long as it's very clear in the context of the problem what substance you're referencing. Now again, I'm assuming you can get the molar mass. It's 12 times 12.01 plus 22 times 1.01 plus 11 times 16. And if I did my math right, actually I bet I looked this up in Wikipedia, I get that many grams of sucrose for every 1 mole of sucrose. And then I want to go, doing the top way, so I'm at moles, and I want to go to molecules here. So I want to get rid of moles. I'm going to put them in the denominator, and I want molecules. And when we're counting which molecules and atoms are a count, we want to use Avogadro's number, 6.02 times 10 to the 23rd molecules of sucrose per 1 mole. Now I need to get myself just a little bit of room here. So let me erase this, and we can go on to our last step. So our last step will be to get to the atoms within. And to do atoms within, we're going to use those coefficients. I want molecules to cancel, so they put them in the denominator since they're in the numerator. We always put it opposite. I want atoms. And that's what this chemical formula means, is that there are 12 carbon atoms for every 1 molecule of sucrose. And assuming, again, I cranked my math out, checked it a couple of times, but if I've done a calculator slip, I am sure you will let me know right away. 1.66 times 10 to the 24th atoms of carbon. And then we are done with that problem. And I'm going to stop the video at this point before we go on to our next concept, which will be the hydrates, working on a hydrate question with this.